morning, everyone. I'm Suzanne Miller. I'm a principal researcher in the SEI Software Solution Division. I am so pleased to be the moderator for our panel on the contribution of model-based engineering and verification to today's theme, Scalable Assurance of Safety Critical Systems. First, let me briefly introduce our panelists. Sam Procter is a senior architecture researcher and the leader of the model-based engineering team here at the SEI, where he focuses particularly on system safety. Jérôme Hugues is the technical lead of the AADL standardization effort. He's been a member of the AADL committee for more than 15 years, authoring many papers around the usage of formal methods to analyze AADL and code generation from AADL to safety critical systems. Sholom Cohen is a principal engineer at the Software Engineering Institute. His interests include software architecture, model-based engineering, and software product lines, and he's done amazing work in all of those areas. He is currently leading the AADL ACVIP, Architecture-Centric verification transitioning effort, supporting the U.S. Army and its contractors. So I want to start with Sam, if I may. Can you quickly introduce the area of research we're going to discuss today? Safety critical systems, assurance, model-based are all sort of keywords in that. What are they, and why are they relevant to our audience?
Sure. So the Model-Based Engineering Initiative develops and applies what we call model-based engineering research results to the DoD and industry. Problems with safety critical systems in these industries, which are those systems that can't fail without hurting somebody or causing a failure of the mission, are growing increasingly expensive and posing larger and larger roadblocks to modern system development. So one particular challenge that we seek to address is that it's not enough for these systems, these airplanes or certain vehicles or medical devices or what have you to work correctly. We have to have confidence that they work correctly, and that is done via a process called assurance. In our work, we rely a lot on the SAE's architecture analysis and design language, commonly referred to as AADL, which is an architecture modeling language that lets us build models of embedded and real-time critical systems. We also use and actually develop here at the SEI its development environment, the open source architecture tooling environment, commonly known as OSATE by its initials. And then we sort of tie all this together in a process that we recommend that AADL and OSATE get used, and that process is called the Architecture-Centric Virtual Integration Process, but is commonly referred to as ACVIP.
So all three of these we're going to talk a little bit about today, and also what Tom introduced earlier, the SAFIR model, or also called SAFER model. At this point, I'd like to get Sholom to talk to us about, regardless of these topics, we need to transition this mindset and the approaches that go with it to DoD customers in real programs. So, for example, how have you applied MBE principles and these approaches in support of the Army Future Vertical Lift program?
Thank you for that question. Susie, what we've been doing actually goes back at least 8 or 9 years to a series of demonstrations that the Army set up called the Mission System Architecture Demos. We've been working with a contractor partner named Adventium, and also with 2 Army people who are at the ACVIP Aviation and Missile Center in Huntsville, Alex Boydston and Bill Jacobs. The initial set of demos was primarily a situation where the SEI and Adventium were performing ACVIP and AADL, as Sam just described, in a shadow effort to parallel the work that was being done by a set of contractors. We did the work that they were doing. We showed how AADL could be used to support the development work, and had a reasonably good success of buy-in from them as to how we would make progress on that. We succeeded. Following on to that was a process called the architecture implementation demos. Mm-hmm. And in situations there was experimentation. It was really a trade space exploration that the contractors performed using AADL in somewhat of an experimental fashion, but also in an applied fashion. One contractor in particular created the architecture and design for a component. They integrated that component with some legacy software and demonstrated the utility of AADL, and in particular to do an analysis that would show that their message set would work. The legacy system could communicate with the new portion of the system, and AADL verified that for them. So there was an assurance case that they developed. ACVIP and OSATE were used to confirm that. The final demo involved a number of contractors. 3 were doing the mission system integration, and the 4th was providing components for that integration. Again, AADL used by all 4. AADL models were produced and then integrated, and we saw an extensive use of AADL in the OSATE tool. Now, over the course of these various demos, there was a lot of back and forth to improve the tool set and the training. So OSATE has matured through a couple of different generations. Getting feedback from these contractors was essential because it was really the first time that non-developers were involved in using these tools. And you get a much different sense of how tools are going to be used when you're dealing with organizations that aren't themselves the tool developers or are not familiar with tool development in general. So we did get a lot of feedback and made vast improvements in the tool set, in particular in the graphical editor portion of the tool. We also developed training, and right now we, as it turned out, when COVID hit in May or March of 2020, we had a course ready to roll out online within a few months. That had been planned to roll out right at that time, and it was really very appropriate that it came. And we put quite a few people through that course, both on the government side, on the contractor side. In addition, we've had some non-government contractors who have taken the course as well. That's available and open to everyone for a small fee, and we certainly encourage people to look into that if they want to learn about AADL. There are also some introductory courses on ACVIP to complement that.
So lots of work in not just the application, but in building transition products like training. And I also know that you've done some things that help contracts and other elements of the stakeholder group to use AADL effectively. Right. So where are you going to apply these advancements in the near term? You've learned a lot. So where is that going to go next?
Well, about 2 years ago, one of the PMs, Dan Bailey, came to the SEI and said, what will it take to get ACVIP, ADL, OSATE, all this technology on contract? And we said, well, it's not just writing a line into the contract. We had some preliminary materials in the form of handbooks, guidebooks. The SEI and Adventium got together and said, this is an approach that we think will work, and we developed what we called an ACVIP plan that contractors and PMs could use together to determine how to get ACVIP on contract, how to use it successfully. And we're right now in the process of transitioning that onto a couple of different programs. So we'll see that come into play over the next couple of years. We have one follow-on activity to look at modular open system approaches, and to determine how ACVIP can be used along with other MBSD strategies to determine, is the system modular? Can we substitute elements from that are currently in the system, pull those out, and substitute new systems in an open system environment? And that's going to be the first trial that we'll use to demonstrate this on actual programs.
Excellent. And I know that there's lots of interest in MOSA and the ability for modeling languages to be able to do what you're talking about, bring a system component in, its description in, and marry it up with other elements that have already been modeled. That's always been a strength of AADL, and this will be an exciting new place to use it. So that's going to be...
The main thing we want to emphasize is the fact that modeling goes with analysis.
Yes,
Analyze,
absolutely.
Can't be sure. So the assurance portion of this is to do the analysis based on the models.
Excellent. So I want to turn to Jérôme now, you're very much involved in the AADL Standards Committee, which is where the language is stewarded, and that and ACVIP or ACVIP are still being evolved. Tell us a little bit about what's coming next for AADL in particular.
Yes, thank you, Susie. So actually, as you may imagine, AADL is, as a standard, has its own life. And actually, we are still evolving AADL because we need to improve the language, we need to improve the tool support. And recently, the group that is crafting the AADL standard has completed a new release cycle for the language. Our objective with this AADL v2.3 was not to change anything in the language itself, but really to make it easier to understand by newcomers. So basically, we have polished many aspects of the language. We have refined some critical sections, like for instance, the semantics of components. How can we lower the bar so that people can understand what is inside AADL, what is the semantics of the language, how to apply it. Another area of work that will be explored by my colleagues in the follow-up talks is how can we apply multi-core systems and modern multi-core systems, with AADL. Our colleagues are developing analysis for AADL, but those are really academic oriented. We have also improved AADL so that we can define what a multi-core system is, so that ultimately we can apply those research approaches on AADL models. And so in other words, basically it's still the same language, but we wanted to make it easier to use, leaner and more agile so that people can use directly the language. And this has been made possible because as we get more people involved in the community, we get a couple of questions. What do you mean by this? Can we provide a better description of that? And all of that contributed to make AADL a better standard, more suited for customers' needs. So I mentioned multi-core systems, annexes, document, etc. All of that makes AADL v2.3 an interesting update to the standard, and hopefully we will enter the ballot phase in December, and we expect publication during the first quarter of 2022.
And I do want to mention again, the annex concept, I think is one of the concepts that makes AADL such a usable standard, because as new things like multi-car, or if a particular processor that's used in airplanes everywhere, for example, is something that we need particular semantics about or particular guidance on using, the annex is a way for us not to change the language, but to improve the utility of the standard as a whole. And so, you know, people that think that it may be daunting to just look at the standard, I would send to the annexes to see if the kinds of things that you're interested in will you know, be helped by some of the language and some of the guidance that's provided there. So you're ready to ballot in early 2022. Say a little bit about what's going on with the environment that contains the tools, OSATE, that the SEI has developed and where it's at.
Oh yeah, I mean, OSATE is really the reference implementation for the AADL standard. So it's a software that is built by the SEI, but used by most industry partners that are willing to adopt and use AADL. Right. So as we are preparing the document for ballot, our engineering team is also preparing for an update of the OSATE toolchain environment with the objective to have a synchronized release of both the standard document and the tool set. And having the tool released synchronously is part of our strategy to transition what we do in terms of standardization efforts so that we can flush all those results directly to potential users and customers. So it's really part of our strategy to transition our activities.
Excellent. All right, so we've kind of done a little bit of a smorgasbord of aspects of transition and the core elements related to AADL and model-based engineering. Let's dive into safety. So Sam, all of the elements we've talked about, you know, allow us to define a system, but not sufficient to fully cover safety concerns. And so why don't you give us an idea, an overview of how we use models for safety analysis and why, and then what kinds of tools are available now, and what are some of those future directions?
Sure. So as far as an overview, I mean, the idea behind using models for safety is similar in a lot of ways to the core idea behind model-based engineering itself, which is that systems are incredibly complex, and that complexity makes evaluation or testing for some desired properties prohibitively difficult or expensive. So what we do is we create an abstraction of a system, that is a model of it, that removes the details that we don't care about, and then that makes analysis simpler. So if we're building an airplane, maybe we don't care what color it is, or whether the screws used to build it are flathead or Phillips, and we can leave that out of our model. What we then have is a simplified model that hides these irrelevant details and lets us focus instead on the things that matter, like if it has redundant airspeed sensors or maybe a backup source of hydraulic pressure. What's cool about most modeling languages, AADL, certainly SysML, things like that, is that if maybe for some wild reason the color of the plane or the screw type does matter for safety, that's okay, because these models and the modeling languages themselves are extensible. So a modeler can really define whatever model they need to support the analysis that they care about. They can not only use them to build models describing the things that we think or other experts think matter, but they can extend that model to include anything that they deem relevant. And one really powerful use of this extensibility is that it supports annotating a system model with information where it's relevant. And this is interesting because it's actually not possible with a straight to implementation approach. That is one that doesn't really utilize model-based engineering technology. So by way of explanation, consider something like a hazard, a known safety problem with a system. While ideally all hazards would be eliminated, some of them can't for whatever reason, and you have to mitigate them instead, meaning that they'll persist in the final version of a system. You can't really write hazard information or mitigation information on something like a fuel hose or an electrical line in your hypothetical airplane. And even if you could, it wouldn't be very useful because you're not looking at those components when you're using them. They're just part of the system. You can, however, add an explanation of a hazard and information about how to avoid it right into the model of the airplane at the fuel lines connector or the electrical juncture right in your model. This serves as really high quality documentation informing or resulting from your safety analysis right where it needs to be to communicate to stakeholders, whether those are subcontractors that are actually going to build this part of the airplane or certification authorities who are making sure that it's safe before we let people get in it and fly, or other stakeholders. So I guess you also asked about the safety tools and the features that are available. Is that right?
Correct.
Right. So I guess here it's important to remember that there are two categories of tools and features available that we've sort of talked about this morning. There's the language, AADL, and then the tool, USATE, that operates on that language. And so we're going to look at the tools and features sort of in those two terms. And in terms of language support, even before we talk about safety-specific features, which I'll mention here in a minute, I want to stress just how useful having a high-fidelity system model is for analyzing a system's safety. A number of simple but unfortunately common problems can be avoided just by getting the basics right. Things like making sure that you're using typed data to communicate between components of a system, and that the sending and the receiving frequencies align so that your sensors aren't spamming too many messages out to your actuators, that sort of thing. Beyond that, we have property sets that we have created and that other safety experts have created that enables system documentation that aligns with major safety standards. So if you're building an airplane and you know that you are going to certify it according to some particular safety standard, we may have that safety standard support built into the language. And then probably the biggest thing that we have in terms of language support for safety is an annex that Jérôme and Susie were talking about earlier, just for modeling errors or off nominal behavior. So this is the Error Modeling Annex. It's in its second revision, so we typically just call it EMV2. And it has too many features to go into in a short talk like this one, but some of the highlights are support for specifying how a fault in one component could occur and then be transmitted to or through other components. And then those components could propagate or transform that error. And these errors themselves have a really rich type system. If you are sort of into this type of error modeling, there's really a lot here. This is informed by both our DoD practice partners as well as a lot of cool work coming out of the academic community. And then in terms of tooling support, we can use these safety standard properties as well as those EMV2 annotations to generate some of the more common hazard analysis formats, things like fault tree diagrams or failure modes and effects spreadsheets that I'm sure if you're a domain expert, you're familiar with and may work with on a regular basis. But we can also find with a partially annotated model undocumented error propagations that might not have been considered fully. And then those can guide future analysis and revisions to the system. So to answer the last part of your question about the future directions for safety and model-based systems engineering, I guess we'll pivot a little bit because there are several new directions here. There are new analyses. There are some usability improvements coming down the pike. And then there's a more integrated approach to assuring system safety that I'm really excited about and that I think is real promising. So in terms of the new analyses, we're always following both what's happening with our users, the feedback that we get from our industrial partners and those inside the DoD, and we've worked with them to support specific needs that they've identified. But there's also a robust safety science community in academia, and several graduate students have developed cool new theories and then implemented their work directly on top of AADL and OSATE so that those research results can transition really seamlessly. In terms of usability improvements, we're always interested in hearing feedback from our users. So if you are a user of AADL and OSATE and you have feedback, please reach out. That helps us improve our tool. Some of this feedback that we get is short-term sort of easy stuff like move this button or fix this bug. But we also get a lot of good ideas about how future versions of the AADL standard itself or major revisions to OSATE could be improved. So there's new stuff there that will make the language and the tool both more powerful and easier to use. And then lastly, some of these changes look specifically at integrating a number of the different parts of AADL, which are essentially different ways to specify system behavior. Often behavior is not strictly architectural, so it's not in the core AADL in some ways, but it interacts with your architecture, and your architecture can change in ways that are sort of driven by the more behavioral aspects of your system. So right now, it can be a little bit awkward to specify behavior in these multiple ways and then run analyses that correctly take into account all of these behavior specifications. But as the different behavior specification techniques get more deeply integrated, we can build much more powerful and predictive safety analyses on top of them, since more of the system itself can be modeled and more of the behavior of the system can be exposed to the underlying infrastructure.
So I've been involved with the ADL for a long time, and I'm very excited about how AADL has gone from let's get the core performance to being able to deal with something as complex as safety analysis and all of the things that have been done to improve it. Now having said that, there's more to know, there's more to research. And in particular, I know that in our own research, we are trying to leverage AADL for assuring the new generation of cyber physical systems. And in particular, we've been focusing on autonomous systems in some of our research. Jérôme, why don't you tell us about SAFER or SAFIR? Depending on where you're from, you may say it differently. But how is that research of ours contributing to this particular area for safety analysis and fault detection, isolation, and recovery?
Yes, thank you, Susie, and thank you, Sam, for setting the landscape for what we are looking at. So yeah, yesterday, IDSHU mentioned that one of the many challenges that the DoD has to concentrate on is trustworthiness. And inside trustworthiness, autonomous systems are creating all types of new challenges. And this is what we're addressing with this project. This 3 years project, we are just finishing the first year, called SAFIR or SAFER, depending on which side of the Atlantic you live in. So what we're addressing basically is the following question. Let's take some autonomous cyber-physical systems. What we want to build through AADL, through model-based architecture-centric approaches, is some global arguments that some autonomous cyber physical system is safe, because we know that we can take a collection of requirements that are properly implemented by some architectural description, by some code, and that we have performed due diligences through verification and validation activities so that the system works. But we know that it's usually not enough. We know that the system is operated safely, and that's why the part of hazard analysis and safety is definitely important. And it is operated in such an environment that we can monitor and monitor for threats, for discrepancies, for faults. And ultimately, we know that we have the proper mitigation strategies in place through some fault detection, isolation, and recovery mechanisms so that we can protect the system itself. And so what we're doing in this project is basically an iteration on what Sam presented and on what I presented on AADL to ask a collection of questions. How can we leverage architectural description so that we can build safer and more secure autonomous systems? So as opposed to many projects, we do not really consider AI system in isolation or autonomous controller in isolation. What we want to concentrate on is on the interplay between an architecture and the AI controller. Ultimately, the AI controller will be in charge of building situational awareness. For instance, if we take this car, can we see all the pedestrians? Can we see the firelight, etc.? All of that will be processed by complex architecture made of sensors, cameras, LiDAR, etc., up to the point where we can build a situation of the system. Between the controller and the environment, there is this complex chain of processing that is supported by the architecture. But the architecture can serve both as a line of defense against faults for the sensors, against cyber attacks, but can also induce particular problems. Timing problems, for instance, if you have a desynchronization between sensors, can mean that the system will be lost to some extent. And so what we are building in this project, and definitely we will say a lot more next year as we are building it, is a comprehensive approach that is leveraging safety analysis, architectural description, and implementation strategies so that we can build a comprehensive approach to support systems engineering, safety assessment, to build and deliver trustworthy and resilient autonomous systems. So that's really a very important project that we're working on. We are improving AADL, improving the semantics of the language, improving the tool support for that, and also connecting with academics partners, for instance, from Georgia Tech, so that we can improve fault detection mechanisms based on some reinforcement learning strategies. So definitely we will be happy to discuss much more on that, either on the chat during the Q&A or next year during the next research review.
And I want to say I'm looking forward to how this evolves, because the safety of autonomous systems. Pittsburgh is one of the cities where autonomous vehicles are being tested. And every time I see one, you know, safety is what comes first into my mind. So I'm really happy that we are working on this frontier so that we can all feel comfortable as these kinds of systems evolve. So thank you for that, Jérôme. I want to move our last question. I want to look at some things that Sholom started to talk about, but I wanted to ask him to give us a little bit more about the research objectives with ACVIP and a couple of interesting things that have come up as we have gone through some of this transition. So Sholom, can you take that for us?
I think, Susie, you actually have a slide to kind of summarize a couple of the points that I wanted to make, which was on the research direction where we're going in the future. And so we've heard from Sam and Jérôme about assurance and safety and autonomy. One of the main concerns that we've had and we've learned from dealing with some of the contractors is the need to consider life cycle issues. One of the problems with these quality attributes of safety and also with timing and with other performance issues is they may tend to think of them as being a late stage kinds of testing activities that go on during the implementation of the system. We're saying, let's look at this from an entire life cycle. From the very beginning of the development, what kinds of safety issues do you expect? What are the interactions between components of the system? How can those affect safety? What kinds of bandwidth do you need, especially when you're dealing with AI, machine learning, processing capabilities? They're really a life cycle kinds of issues. And how do we bring ACVIP and AADL into that picture. One question in particular is how do we do modeling with analysis? Philomena Zimmerman, I recently heard her make the statement, we don't want architecture as artwork. We just want to have pretty models that we can look at and point to. We want to have models that go with the analysis and say this system is assured that it will work in this way, or that we know that there are these gaps that we need to close. So we want to make sure that ACVIP and the language and the tools are used to do early stage modeling and analysis for these various areas of safety, behavior, performance, and so on. And finally, we want to be able to move modeling and analysis to the right. So we don't just, to the left. Right now it's on the right. It's at the end of the life cycle, end of the timeline of system development. We want to see what can we do early in the development, point out these problems and uncover defects that would not be discovered until late in development. And we've seen in the experiments and tests and demos that we've done so far with contractors or with the Army that we can find problems early. It's just a matter of applying modeling and analysis early in the process. So I summarized in the table below that we can do trade-offs. We have models that can be reused across different systems. We can trade off and find different and alternative examples and consider those in a system. We can also do a refinement of specs, and we've done some research already into looking at the specification as it comes from from the government in a software specification document, and say there are maybe some gaps, there may be some inconsistencies, and maybe some new information that a contractor would make assumptions about. How can we close that assumption gap and make sure that the information that the contractor is applying to fulfill that specification is the real intent behind the government's need for that particular capability? And of course, we want to do early defect detection. We don't want to wait until the test phase to find problems during operation or even late in the integration and testing. We want to find them as early as possible so that we can mitigate against them. Now, if we go to the next slide, one of the things that a lot of times occurs is program managers, either on the government side or on the contractor side, say, well, I like all this modeling and I think it's going to produce good results. But isn't that going to increase the costs and slow down the schedule and interfere with actually getting work done? And what we found during Capstone was that an interesting result. One of the contractors produced this chart. I just annotated it to show, highlight a couple of points on the chart, but they produced this chart and they said, if we knew now what if we knew for a future program what we do know now, we would have applied this analysis early in the process and we could have saved a lot of downstream costs. Now, this is a cost-related chart, but I think we could say it's also a defect-related chart and a quality-related chart. So the assurance comes at the end because we put investment up early in the process. Modeling and analysis that we do early can show great benefits at the end of a program. Whereas if we do modeling without analysis, or we only do the analysis at the end, we're not going to be able to achieve that sort of benefit. So our feedback to the contractor community and to the government community is consider these activities early in the life cycle when the cost of making repairs is small, and you'll save making repairs later. And it applies whether it's safety issues, whether it's performance and timing issues, whether it's memory utilization, all those types of issues can be analyzed early in the process. You can make sure that you're addressing your requirements adequately. You can make sure that you're meeting schedules and deadlines appropriately. So that's really where we're going, and we're applying some of the lessons learned from these programs to make this an assured for future development.
And I am so excited to see this last graphic because I know so many people have been asking for a long time, how do we know that this is actually helping us? And we are at a point where we have that data, and that is very exciting for our future users as well as current ones.
We really need to transition it from the safe science and technology area to say yes, no operation.
Absolutely.
And that's the real challenge going forward.
Oh, we all know that. All right. This has been a whirlwind tour through the safety supporting research that the model-based engineering team is doing to both enhance our understanding of complex cyber physical systems through their research, and to enable DoD and other stakeholders building complex cyber-physical systems to take advantage of model-based engineering approaches, AADL, OSATE, in developing and delivering safe, scalable, complex systems. So feel free to reach out if you have additional comment or questions that we can't take in the time that we have left to us, because collaboration, as you've heard throughout this presentation of the panel, is what makes for successful MBSE adoption. I want to thank all of our audience for joining us today. I think we've got time for one or two questions. The first one for Jérôme was, how can I get the document to add new annex into OSATE as a new tool? I would really appreciate that.
Yes, I mean, if you have any question with regard to the tools, we have a website, osate.org, that is providing all the information and the mechanisms to reach out to us. So feel free to send an email to one of the mailing lists, and we will assist you in this process. It's some implementation work based on Eclipse, and yeah, we are here to help for this type of question, of course.
Okay. And the second question, are you planning to or considering integrating the results of the DARPA ARCOS project in your MBSE environment? And I believe that one is for Sam.
Yeah, absolutely. We are tracking ARCOS closely, and we're excited about the results that are coming out of that. So there are a couple of ways that integration might happen. The first is that depending on the results of ARCOS, we maintain OSATE. We have a number of OSATE developers, so we can look at an SEI internal effort of integrating those results either in concert with a specific customer who's interested in one or more of the approaches that ARCOS pioneers, or as part of a research project like Sapphire that Jérôme talked about earlier. The second is that, as I mentioned earlier, we sometimes see specific research ideas get implemented by academics or companies outside of the SEI directly into OSATE. So since AADL is developed in an open committee, OSATE is open source. You can actually download, play with, modify it right now off of GitHub. We often see these research advancements released by others. And so I'm always optimistic that in research projects like ARCOS, we can see those sorts of plugins get created directly. And then, here at the SEI, we're happy to work with whoever is doing that and make sure that OSATE is amenable to that sort of modification.
Thank you, Sam. Thank you to all our panelists for all the hard work that goes into taking such a large body of work and turning it into a 45-minute presentation. So I want to thank all of you, and thank you for our audience for questions. Please address any other questions. info@sei.cmu.edu always works. And I will turn it back over to our hosts. Thank you.